All right, welcome back to our fourth and final video on portfolio optimization. So in this video, I'm going to show you how we actually optimize a portfolio. And I could do this in R, I could do it in Python. For our sake, I think it's probably best we just do this in Excel. It's way easier to really get an understanding of. So that's what we're going to do. So our agenda in this video is very, very simple. I'm going to show you one example, and that example is going to involve me optimizing a portfolio using the entirety of modern portfolio theory. So here's our scenario. We have two risky assets we can invest in, Lockheed Martin and Alphabet, or ticker symbol Google. Now, you can also purchase unlimited amounts of a one-year T-bill. We know our utility function, and that utility function is the expected return of our complete portfolio. So, return on our portfolio and our return on our risky asset portfolio. And then minus 1/2 coefficient of risk aversion times variance of our risky portfolio. Coefficient of risk aversion, we're going to set that at 3. For context, 3 is a very high coefficient of risk aversion. And we're going to complete the 2 steps of modern portfolio theory. So in step 1, we're going to identify the ideal weights of our stocks in our portfolio. And in step 2, I'm going to identify the ideal allocation to the risky portfolio and the risk-free asset. So I'm going to move over to Excel for the rest of this video, and we'll get going. Okay, so I'm over here in Excel, and I've set up our, the basic data that we need to complete this problem. We have our coefficient of risk aversion. I said it was 3. And then we have all 3 pieces of data that we need for modern portfolio theory. We have expected returns for all of our assets. We have standard deviations for our risky assets. Note that the standard deviation of a T-bill is 0. And our correlation between our 2 risky assets is here. I could also calculate the covariance if I wanted to. Covariance is just correlation times standard deviation of 1 times standard deviation of stock 2. There we go. Okay, let's start with the first step of modern portfolio theory, the security selection step. This is the step where we maximize our Sharpe ratio and identify the ideal weights of our 2 risky assets, the stocks, Lockheed Martin and Google. Now, to get our Sharpe ratio in here, we do have to calculate the portfolio mean, the portfolio standard deviation. So I'll just do that now. So, we have our weight of stock 1 times our return on stock 1 plus our weight of stock 2 times our return on stock 2. I'll tell you what, I'll leave the variance blank for right now. In fact, we don't really even need our variance. We can just, take standard deviation squared later on. But our risky portfolio standard deviation, I thought it'd be helpful just as I'm going through this so you can see what I'm doing. This is the formula we use for our portfolio standard deviation. So maybe I'll put it up here so you can actually see it as I type. So equals square root of the weight of stock 1 squared times the variance of stock 1, so standard deviation squared, plus the weight of stock 2 squared times the variance of stock 2, so standard deviation squared, plus 2 times the weight of stock 1 times the weight of stock 2 times our covariance. I could have alternatively used, instead of covariance, correlation times standard deviation times standard deviation. Simplicity is good, though. Okay, so there we go. Now, to get our Sharpe ratio, we just take the Sharpe ratio formula, just the return on the risky portfolio minus the risk-free rate up here, divided by our standard deviation of our portfolio. There we go. Now, this is the thing that we want to maximize. We want to find the portfolio that has the weights that give us the highest Sharpe ratio. And the Sharpe ratio, it's directly linked to these weights. So as these weights adjust, what you're going to see is that the Sharpe ratio will adjust. All right. Now, to optimize this portfolio, I am going to need Solver. Like I said, I could do this in R, could do this in Python, but in Excel, we need to use the Solver optimization tool. So I'm willing to bet a fair number of you have used Solver before, but if you haven't, this is how we kind of identify, or in Excel, we can minimize, maximize, or get to a value that we want. So we typically are going to have an objective cell, and in this case, our objective is to maximize our Sharpe ratio cell. So there we go. And we want to maximize it subject to certain changing cells. Those changing cells are going to be our weights. So what Solver will do when I click Solve is it'll find the ideal weights that maximize the Sharpe ratio, and it'll change these weights to the ideal weights. Now the final thing that we need to put in here is some constraint. If I were to click Solve right now, what you'd see is that we'd get some really funky stuff because, first thing that Solver is going to do is it's going to dramatically increase these weights. Why? Well, because that'll get us a higher and higher Sharpe ratio. So we need a constraint to tell Solver that we want the sum of these weights to be equal to 1. So let me just add a constraint. And what I've gone ahead and done here is I've built in this cell, the total cell, and what this does is it takes the sum of these two cells. So if you were to look in this cell, what you'd see is that the formula in it is sum of C14 and C15. Okay, so I'll set this equal to 1 or 100%. Click OK. And now we have everything we need. So if I click Solve, Solver found a solution. All constraints optimized, or constraint optimality conditions satisfied. So here we go. Our ideal Sharpe ratio is right here, 0.1234. The ideal weights for that Sharpe ratio are a little different than our equal weighting, 27% in Lockheed Martin and 73% in Google. So we have just completed the security selection step of modern portfolio theory. We identified the ideal weights to our risky assets. This is the step that is most commonly used in the real world. Now, people might not use Excel to do this, but they are using some kind of solver-like program to do this. Now, the second step is the step where we identify how much of our total wealth we allocate to the risky portfolio versus the risk-free asset. And I've already gone ahead and put the formula that I had from our last video right here. And what we're going to do is we're literally just going to plug and chug. I mean, I talked about if you want to see the derivation for this, take a look at our appendix slides and you can see how we get to this. Basically, we just assume a utility function and then derive the weight to the risky portfolio. So here, we're just taking the return on our risky portfolio minus our risk-free asset return, right there, and then dividing by our coefficient of risk aversion times the variance of our portfolio. Coefficient of risk aversion right up here times the variance of our portfolio. So standard deviation squared. There we go. And the weight to our risk-free asset is just going to be 1 minus that. So what this is telling us, and it's not perfect here, I mean, it rounds nicely, but basically, to maximize our utility in the second step, what we would do is we'd put 9% of our total wealth in the risky portfolio and 91% of our wealth in the risk-free asset. Like I said at the beginning of this example, this coefficient of risk aversion is pretty high. It indicates that I'm very risk averse, and admittedly our T-bill yield is, I mean, it's pretty good. It's close to our return on Lockheed Martin stock. So this result does not surprise me. So with that, I'm going to bring this video to a conclusion, and if you have any questions, please feel free to reach out. Thank you.